Hi guys, hope you're having a wonderful day so far. Today we're going to talk about heating and cooling curves for water. And so a heating curve or a cooling curve is where you show the temperature in Celsius on the y-axis and you show either heat added or heat removed or time or something like that. So I know that you talked about this in physical science. Some of you might have even done an experiment where you took some really cold ice, started heating it slowly, and saw what happens in terms of temperature. So if you get some really, really cold ice, lower than its freezing point, which we know you can have ice that's colder than freezing point, like when it's 20 Fahrenheit, that's lower than the freezing point of water, right? And you have ice and snow out, it's at that cold temperature. So when you heat up really, really cold ice, the temperature starts rising until you hit 0 degrees, which is the melting point. At that point, you start seeing that the ice starts to melt, and even though you keep heating it, the temperature doesn't change. It keeps steady at 0 Celsius until all of it melts completely. And then if you keep continuing to heat, after it all melts, then you see the temperature rise and rise and rise again until you hit 100 Celsius. And then at 100 Celsius, it starts vaporizing. You see boiling, and the liquid water turns into gaseous water. And while that's happening, you don't see any temperature change either. So both phase changes, the temperature kind of plateaus until it all vaporizes and turns into gas at 100. Now, if you were to trap that gas somehow, I'm pretty sure you didn't do that in physical science, trap the gas somehow and heat it up some more, you will see that you can actually heat up that water vapor to higher than 100 Celsius, higher than its boiling point. So I'm going to show you a demo where I heat up some water vapor and turn it into a much higher temperature. So see if I can adjust my camera here. I have an Erlenmeyer flask right here that I have water in it, and it's heating up. And so the water is boiling, and I can see bubbles here. Turn up the heat a little bit more. And so right here, the water is boiling, and the liquid water is turning into gaseous water, and that gaseous water is traveling through. My stopper has a copper coil through it, copper tube, and so I don't know if you can see that there's a little bit of steam right here. I'm not sure if you can see it or no, but there is some steam here. Now, the steam that I see, and again, I'm not sure if you can see it very well. You don't see it right here, but you do see it here. Or if you've ever cooked at home and looked at your boiling pot, you don't see any steam right at the very top of the liquid, but you do see steam above. This right here, if you can see it, right there, what you can see is actually condensed liquid water. So there you don't see anything because it's too hot. It's actually a gas. But here, if you can see it, this is water vapor that has condensed. When it hits the cold air, it condenses back and turns into little droplets of liquid water. So what I'm going to do next is I'm going to light another Bunsen burner, and I'm going to heat up my gas that is trapped in that copper tube. So I'm going to go ahead and heat this up. And I'm going to go real quick grab a piece of paper to show you how hot that gas is. And I don't know if you were able to see the steam before, but now the steam has disappeared. We don't really see it anymore. That's because that steam that's coming out is really, really, really hot. It does not condense until way, way later. So we don't see anything. That's what's really dangerous because it's extremely, extremely hot. And I'm going to show you how hot it is. I'm going to put a piece of paper right here. I'm not going to let it touch. I don't know if you can see that, but I burned a piece of paper by applying steam to it. That's very, very, very hot. Remember the book Fahrenheit 451? Fahrenheit 451 is what? Some 200 and some Celsius, so that's way above the boiling point of water. And again, just to show you how hot it is, I'm going to light a match using that steam. See that? So it's extremely, extremely, extremely hot. So you can heat up a gas definitely above its boiling point. All right. So let's go back to our diagram here and try to talk in detail about what actually is happening to the particles and in terms of energy. So we're going to start with the ice that is pretty cold, so ice at lower than 0. And I'm going to show a particle diagram for it. So since right here, this is a solid below 0, I'll go ahead and see if I can write that down. No, I can't. Sorry. Okay, so this is solid at below 0. And because it's a solid, the particles are really close to each other. They're nice and ordered. And because it's so cold, it's moving pretty slow. So I am showing, this is just my own notation, I am showing the speed of the particles using these arrows. The smaller the arrow means the slower it is. The bigger the arrow means it's fast. I also have some amount of kinetic energy and potential energy in there. I put one box of each. That does not mean that they're equal to each other. It just means I have some certain amount. So this is qualitative, not quantitative. So I'm going to take that solid and I'm going to heat it up. And if I heat it up, my temperature increases. Temperature is related to kinetic energy. So along this line, I want you to write increase in kinetic energy. As I go from solid below 0 to solid at 0, I'm increasing my kinetic energy. So if I'm increasing my temperature, I'm increasing my kinetic energy, which means I'm increasing my speed. So it's still a solid. They're still close to each other, so the position didn't really change. But I have increased my kinetic energy, which means my particles are a little bit faster. So this is how I'm going to show it as a diagram, as a particle diagram for what's happening here at solid at 0. So still close to each other, still in this nice ordered crystal, but my speed is a little bit higher because I've increased my temperature, which means my speed of the particles have increased. As I go from solid at 0 and keep increasing the heat, keep heating it, I start to see it melt. So along this line, I want you to write melting. And the temperature seems to plateau when we're going through a phase change, even though we're heating it. And so my temperature remains at 0 all the way until it all turns into a liquid at 0. So when I have my liquid at 0, now my particles are still pretty close to each other, but not as organized. So I'm just going to show them kind of close to each other, but not as, not in a nice crystal. And because I did not change my temperature, my speed here versus my speed here should be the same. If my temperature is the same, that means my kinetic energy remained the same. So if I'm heating it and I'm not speeding up the particles, then where is that heat going? How come I'm heating it and my temperature is not changing? My particles are not speeding up. Well, that heat that I'm adding is going into potential energy, meaning that I'm changing the position of the particles. See how here I had this nice crystal? I use that energy to break that crystal so that the particles are able to slide around each other. So potential energy, positional energy. So along this line, I want you to write increase in potential energy. I'm increasing its potential energy, not its kinetic energy. So my temperature remains the same, my speed remains the same, but my position changes. Okay, as I go from liquid at 0 and I keep heating it, my temperature starts rising until I reach liquid at 100 Celsius. So it is still a liquid. The position of my particles is pretty much the same. I didn't really change the position. But if I'm changing my temperature, if I'm increasing my temperature, that means the particles are moving faster. So I'm going to use faster arrows here. So now the heat is going into changing my speed of the particles, my kinetic energy. So anytime there's a temperature change, that tells you there's a change in kinetic energy, in the speed of the molecules. So along this line, I want you to write increase in kinetic energy. Okay? As I go from liquid at 100 Celsius and I keep heating it, it starts vaporization or evaporating. So I want you to write along this line evaporation or vaporization, and it's turning into a gas at 100. And again, we see the temperature not changing when we have that phase change, even though we're adding heat. Well, why? If my temperature is not changing, that means my speed is not changing, right? So what is happening? Where's that extra energy going as I heat it? Well, it's going into potential energy again. Whenever you have a phase change, you're changing the position of the particles. So I'm turning it from a liquid where the particles are pretty close to each other into a gas where the particles are really far apart. And that change in position requires energy in order to separate those particles because they're attracted to each other, right? So my position changed. So along this line, I want you to write increase in potential energy. But my kinetic energy is the same. My temperature is the same. And so my speed of the particles is the same as well. So I'm going to use the same sized arrows as my liquid at 100. So if you're at the same temperature, your kinetic energy is the same. Your speed is the same. And then finally, as I take this gas and heat it some more, just like we saw with our super steam demo, you can heat it up to a higher temperature, higher than its boiling point. And so it is still a gas, so the particles are still pretty far apart from each other. But because I changed my temperature, that means that my particles are moving faster. So I'm going to use faster particles. And to show that, I'll use my bigger arrows to show it. And so if I'm increasing my kinetic energy, that means I'm changing my temperature. So along this line right here, going from gas at 100 to gas at above 100, I want you to write increase in potential energy. Let's look at these boxes. So actually, I'm going to go to the next slide here where it's showing all this stuff. So this is solid at 0. And as I increase the temperature to go to solid, this is solid below 0, this is solid at 0. So my position of the particles is the same, so my potential energy is the same, but I have increased my temperature, that means my kinetic energy is the same. So I chose to put like just another box there. So as I go from here to here, I'm increasing kinetic energy. As I go from solid at 0 to liquid at 0, I've changed the position of the particles, so my potential energy increased. So along this line, there's increased potential energy, so I put another box there. But my kinetic energy is the same. I can tell that because my temperature remains the same. So speed remains the same, but position of the particles changes. As I go from liquid at 0 to liquid at 100, my temperature increased, which means the kinetic energy increased. So I put another box there of kinetic energy. So along this line, there's an increase in kinetic energy. My position of the particles is about the same, and so my potential energy is about the same. So I've increased my temperature, meaning I increased the speed. As I go from liquid at 100 to gas at 100, my temperature remains the same, so my kinetic energy is the same, but I have increased the potential energy, so I added one more box here to show that the position of my particles changed, And so that energy went into separating the particles and keeping them far apart as a gas. So as evaporation happens, I'm increasing my potential energy. And then finally, as I go from gas at 100 to gas at above 100, my temperature is changing. It's increasing, so the speed of my particles is changing, so my kinetic energy is changing. So I add another box, but my position of the particles is about the same, and so my potential energy remains the same. So I might ask you on the test to sketch a heating curve for water. So you would do temperature versus heat added or time. You would draw this curve right here, or lines. I might ask you to label the phase changing, the melting, and evaporation. I might ask you to label which lines involve change in kinetic energy, which lines involve an change in potential energy. I might ask you to draw particle diagrams. I might ask you for each of these points, is it a solid, liquid, or gas, and so on. I could also ask you to do a cooling curve. So a cooling curve would look the same, except backwards. So you'd have very, very hot steam at above 100. You'd cool it down, so it'd go to gas at 100. Then it would condense to go to liquid at 100. Then the temperature would drop to get to liquid at 0. And then you would freeze to get to solid at 0, and then the temperature drops again to get to solid at below 0. So here's the exact same thing that I just did, but with the cooling curve. And so along this line, and this line, that's a decrease in kinetic energy. I know that because my temperature is dropping. But along the flat lines where condensation happens and where freezing happens, that's a change in potential energy. My potential energy is dropping because my particles are getting closer to each other, so it's releasing that extra heat or extra potential energy. All right, have a wonderful day, guys. Bye.